Hello, my name is Roy Simpson, Professor of Mathematics at Columbus River College, and in this video we're going to talk about how we're going to estimate the value of sine of x over x, or maybe I should say how we can investigate how close x can be to 0 so that the value of sine of x over x is really close to 1. This is really investigating the precise definition of a limit. Now, the point of this video is not to actually go into and prove this limit using the precise definition of a limit. Instead, it's to investigate the structure of the precise definition of a limit. So in your calculus course, you probably or should have already talked about the precise definition of a limit. I'm going to go ahead and write it here. I'm going to use symbolic logic language. So the precise definition of limit says the following. If somebody hands you a statement, limit as x approaches a of f of x is equal to L, what they're truly saying, and what this really means behind the scenes, and we have a conceptual understanding that this means that our function values get very close to L as x gets very close to a, but not equal to a. However, that's a conceptual understanding. The true understanding is this. For any epsilon that somebody hands me that's positive, we should be able to find a delta also positive so that we know that whenever x is really close to a, how close? Within this delta neighborhood. So that 0 being less than the absolute value of x minus a being less than delta, that is, x is really close to a, again, within a delta neighborhood of a. The 0, by the way, is there to ensure that x cannot actually be a. But that will imply the distance between your function and your limit is less than epsilon. Or in other words, your function is within an epsilon neighborhood of your limit, L. So that is the symbolic mathematics way of writing it. Now I'm going to go ahead and trade that out just for the language. The language that upside down capital A says for all or for any, and then epsilon, that's positive. The backwards capital E says there exists delta, that's positive, so that or such that if x is in a delta neighborhood of a but not equal to a, then our function value, our y values, is within an epsilon neighborhood of L. They say the same thing. This is just the language of the precise definition of a limit. All right. So that's what we're going to investigate here. Visually, by the way, I always find that it's good to kind of throw on a visual as well. So let's go ahead and magically throw down a visual here. And I'm not going to actually graph our current function because I don't think that's going to be worthwhile. I'm going to graph just a random function. So let's pretend that you have a random function here that at x equals a, it has a jump, what we would call a jump discontinuity. Not that big of a deal. Okay. And let's pretend as though the value that it could have been as x was getting close to a is L. So what an epsilon delta, or what the precise definition of a limit is saying is that somebody comes up to you and says, listen, you have an epsilon neighborhood that's centered at L, some neighborhood along in the y values that is symmetric and centered at L. So somebody says, for example, I'm giving you this epsilon neighborhood. Again, it's centered at L, so it'll be symmetric. The height here is L plus epsilon. The height down here is L minus epsilon. So you have a little wiggle in height. And our job, so that's what somebody hands you. We're given. That's why it's stated in the theorem that we are given some epsilon greater than 0. So for any epsilon greater than 0 means that somebody's handed us that. So somebody's come in and handed us this epsilon. Our task is to find the delta. So I'm going to go ahead and highlight this in blue. our task is to find that delta, our delta neighborhood, so that any x value from our delta neighborhood lands between these two bars. In fact, I will go ahead and highlight between these two bars here. I need an x neighborhood that's centered at A, such that all x values in that neighborhood yield y values that land in this epsilon neighborhood. So you can kind of visualize this. I'm going to use red, even though usually red is kind of associated with bad. I'm going to use red just to showcase what I would think is a good delta neighborhood for this. So remember, it's going to be symmetric about A. So it's the same, should be the same distance on both sides. Okay. And notice that any x value from that neighborhood, so here's my neighborhood right here, centered at A, any x value from that neighborhood, aside from the x value of A itself, because remember, we don't really care about A itself. We care about just x values within that it belongs to this neighborhood, except for at the center itself. So I'm going to not include the center here. Okay. But all the x values that I've highlighted in green, they lead to y values that are between the horizontal bars L minus epsilon and L plus epsilon. So let me go ahead and shade all the y values that my x values lead to. Notice they're between a height of L minus epsilon and L plus epsilon. So that's the ultimate goal. If I would have chosen, by the way, and let me zoom in so we can see this. If I would have chosen a wider delta neighborhood, that'd have been bad, really bad, in fact. So let me showcase that. So there's some remnants of my previous delta neighborhood, but don't worry about that. Let's just suppose for now that I chose a delta neighborhood that was this wide. So remember, it's supposed to be the same distance on both sides. So here's my symmetric delta neighborhood. If I chose a delta neighborhood this wide, drawing this out, notice that there are some x values here, like all of these guys. All those x values lead to y values that are actually in our epsilon neighborhood. However, on the right-hand side, while some x values do still lead to y values in our epsilon neighborhood, there are some bad x values that lead to bad y values. They're y values outside that epsilon neighborhood. So that delta neighborhood that I've chosen is way too wide because some of the y values are outside the given epsilon neighborhood. Again, let me reiterate that the center is something we're ignoring. With limits, you could care less about this center. I care less that at x equals a, it's outside of the epsilon neighborhood. That's not of import to us. What we are more concerned with is that as x gets super close to a, but not equal to a, that the y values are within this epsilon neighborhood. But at a itself, we don't care. Okay, all that being said, going back to the original question, which didn't sound like a limit question, but it actually is, saying that we're going to allow x to get really close to 0. So that's kind of this statement that I will highlight right now. It's this statement. X is getting really close to something, and we want our function values to get really close to 1. How close? Well, in this case, they're telling us within 0.03 of 1. So what I'm going to do right now is go ahead and visualize this, first of all, using a graph, because this cannot actually be done very easily, in fact, at all, using an epsilon-delta proof for a limit, but we are visualizing the epsilon-delta proof with this example because it's a very famous example and it's good to see this. So what I'm going to do is graph the function sine of x over x using free software, free online website called Desmos. So what you're visualizing right now is just the website www.desmos.com. It's a free website, and I met one of the programmers for this site, or one of the developers for the site, and really nice guy, and a really good kind of company as I see it. So I'm going to go ahead and put in here the function, and you could use y equals, but I'm actually going to go ahead and type in f of x. So I've typed that in, and I'm actually going to go ahead and hide that list for now. What I want to do is zoom in here and maybe move this around. Now we're going to let x get super duper close to 0. And you can see actually for this function, as x gets really close to 0, it looks as though the y values are approaching 1. And in fact, they are. But I'm going to go ahead and make it more interesting, because in our problem that we're given, they have given us that that the y values, the function, has to be really close to 1. How close? Well, they've handed us an epsilon neighborhood. Let me go ahead and point an arrow at that. That 0.03 means that they've given us a wiggle size in our y values of 0.03. So we want the y value wiggle to be 0.03, and our true y value that we're approaching is 1. So I'm going to go ahead and graph that. I'm going to graph 1 plus a 0.03 and 1 minus a 0.03 here. So I will go ahead and add an item, and I will say y equals the 1.03. So it's supposed to be a 1. And I will also graph y equals 1 minus a 0.03. Now, if you look at this graph, that is really hard to see, but you can see my epsilon neighborhood. In fact, maybe I'll put on a different color here for those. I'm going to go ahead and let my function be black here, and I'll let those bars be red so that they're easy to see. And on top of that, I'm going to change my window. This is just to showcase kind of how you would do this. I'm going to change my window to go from, let's pretend, because we're really interested in getting close, our x values close to 0, I'll modify this so these x values are close to 0. All right, so what you can see is that I've adjusted the x-axis to go from negative 0.5 to positive 0.5, and the y-axis, just so I can zoom in a little bit, I have the y values going from 0.8 to 1.2. I'm going to go ahead and take off the minor grid lines too, just so it's a little bit easier to see. And here we have it. It's very nice. I can actually zoom in just using my fingers here so that you can see that. So I want to know how close do my x values have to be to 0 so that all my y values exist within this epsilon neighborhood. And I just switched browsers really quickly because I want to be able to highlight on this. So we are looking at all the x values that lead to y values in this neighborhood here. And you can see I'm just highlighting the y values that are in our epsilon neighborhood. And you can kind of see actually where the x values start and where the x values end. I'll use a different highlighting color for that. I'll choose that color right there, and I'll use a dot. You can see we have from that x value to that x value. Those are the x values I'm interested in finding out what they are, so that I could say, okay, well, I need my y values to be in this neighborhood. So what x values that are close to 0 will lead to that? So now I'm going to go ahead and use, again, you could use a graphing calculator for this, but Desmos does a pretty decent job. I'm going to look at these intersection points. And if I just tap on the black curve, you'll see it actually shows you what these values are. I'll tap on that piece too. So you can see that the intersection points, those x values are negative 0.4262 and positive 0.4262. So I know that as long as x is between negative 0.4262 and positive 0.4262, all the y values will actually lead, or will all those x values between there will lead to y values in this epsilon neighborhood. So that's a good visualization of an epsilon-delta proof, or basically the precise definition of a limit. Now, the bad thing, or one of the bad things about Desmos, is that you cannot control, as far as I know, the accuracy of the data. So in other words, you cannot say how many digits you want. So if your instructor is looking for 5 digits of accuracy, well then you're going to have to use a graphing calculator or something like that. But the idea is still the same. Graph the function sine of x over x, and then graph the epsilon neighborhoods, which are 1 plus 0.03 and 1 minus 0.03, and find their intersections. But what I'm going to do is write on here, so how close must x be to 0 to ensure that our function is within 0.03 of 1? Well, to answer that question, so for the epsilon value of 0.03, we need delta, which is supposed to be a positive, delta neighborhood. And remember, it's a radius neighborhood, so delta to be less than 0.4262. And I say less than because you want to be, you definitely want to be conservative with your estimates. So 0.4262 is what I'm going to put here. We need delta to be less than 0.4262. Now, a lot of people will just say let delta equal 0.4262, but I think it's probably better to say let delta be any number less than that. And so our delta neighborhood, if you really want to showcase the delta neighborhood, you would say the delta neighborhood goes from negative 0.42, and I'm going to round to 3 decimal places, negative 0.426 all the way to positive 0.426 because it's centered at 0. Another way to write this, by the way, is to say that we require the distance between x and 0 to be less than 0.426 or 4262 if you want to do 4 digits. So that is saying the distance between x and 0 has to be less than 0.426, or x is within 0.426 of 0. So I can then highlight on the x-axis the values from roughly 0.4262, negative 0.4262, to positive 0.4262. So those x values roughly will lead to y values within our epsilon neighborhood. Now, if somebody changes up the game on us and they come back here and say, you know what, never mind, I want to do that problem over again, but this time, instead of an epsilon neighborhood of a 0.03, I'd like an epsilon neighborhood of a 0.001 or 1/1000th. Well, it actually will not take that much work. I can just adjust my graph. So I'm going to write the language first. For epsilon being 0.001, in other words, for a very small epsilon neighborhood of a 1/1000th, what do we need for our choice of delta? Well, let's go back to the graph. Here we go. Let's go ahead and change these y values here. Instead of 1.03, we're going to have an epsilon neighborhood of a 0.001. So I want 1 plus a 0.001. So I'm going to write 1 plus. Obviously, you don't have to write the plus in there. You could have just written 1.001, but I'm just showcasing the idea of an epsilon neighborhood, and 1 minus 0.001. Of course, you do this, and you'll see that you need to zoom in quite a bit to actually see this neighborhood. We keep zooming in here. And there you have a nice neighborhood, although you cannot see very easily. That's definitely my epsilon neighborhood, right? I have to zoom in quite a bit to see it. But now we need to know what is our associated set of x values that lead to those y values. So let me go all the way over to the left here. And obviously, probably a good choice to do is to just move my window to help out. But you could see that here's where x values, and let me highlight this. Here are the x values lead to y values that are below my epsilon neighborhood. Here we have x values that lead to y values that are within my epsilon neighborhood. So I definitely want to know, where does this graph of sine of x over x intersect that lower epsilon bar, so that I can know when do I start my x values. So let's go ahead and readjust our window and find out when those intersections occur. I can see actually down below, by the way, it's 0.08, but let me or roughly 0.08, but let me zoom my window and adjust things for that. So all I did here was I went ahead and just clicked on a black curve, and it shows me the intersection point. Notice it says the intersection point's 0.999. It's lost a little bit of well, actually, no, that's accurate. So what I'm going to do is get my window to kind of capture this negative 0.077, where and then likely due to symmetry to positive 0.077. I'm going to go from negative 0.08 just on my window so you can see this to positive 0.08. So let me type that in here. Negative 0.08 to positive 0.08 so that we can see what this looks like. Get rid of that. And there we go. And so you can see the intersection points. Let me go ahead and tap on the black curve there and tap right there. So I can see it's a symmetric neighborhood. My delta neighborhood to get within this epsilon neighborhood is going to be a negative 0.077 to positive 0.077. And I'm shrinking those numbers so that it's a little bit better. So in other words, I'm not really being super duper exact. I'm tightening up the delta a little bit just in case. I'll showcase that right now. So let's say I went from negative 0.077 rather than 0.774 or whatever, all the way to positive 0.077. It would be that as far as the x values that are associated on the x-axis with those x values right there. And it still keeps us within our epsilon neighborhood. So tightening up the delta neighborhood a little bit doesn't hurt. It is okay to do that. So again, going back to the original graph here, I'm going to go ahead and just make sure that I highlight the proper value. So here we go. Okay. So negative 0.077 to positive 0.077. So 0.077. As long as I'm within that, I'm okay. So again, negative 0.077 to positive 0.077. Or in other words, the distance between x and our center, 0, must be less than 0.077. And I should, just to be clear, state that we cannot actually let x be 0. That's just part of a precise definition of a limit. We could care less about x being at the center. We just care about x being near to that center of that interval. So this is a good example of what you do when somebody hands you an actual concrete value for epsilon. You would graph those epsilon bars and then use intersections to help you find out what the corresponding x neighborhoods are. One thing I should note here is we were lucky in this case that our neighborhoods were symmetric, right? The x value on the left and the x value on the right, those distances were exactly the same. That would not always be the case. So if you have a case like this function right here, which I don't know what it is, notice that really, if you wanted to know what x values would work, it's this x value right here all the way to this x value right there. So this would be one choice of delta right here. Let me just write this down here, delta sub 1. And here would be another choice of delta, delta sub 2. And again, you will always be okay with choosing a smaller delta, and in this case, I would choose my delta to be delta sub 2, because if you chose your delta to be delta sub 1, because you need your interval to be symmetric, you're saying, I'm okay with all these x values, and again, if you chose delta sub 1 as your delta, you would say, and all these x values, because it has to be symmetric on either side, and that's just not good. That's a bad choice. So tightening up the delta and saying, listen, I'm going to choose my delta to be this smaller delta, guarantees that your x values lead to y values within your epsilon neighborhood. So always choose a smaller delta. That wasn't part of this example, but it's worthwhile to mention.